So hi everyone, and thank you for everyone to join and also for the online audience. Also, at least thanks for waiting up very early. So let me minimize this Zoom to not. So the major elements of my PhD is about nonlinear mechanics, and I included it in the for the modeling and inversion of earthquakes. Why we do earthquake modeling? This is because of the earthquake hazard that we all from time to time need to. Okay, sorry, it's not working. Yeah, we need to deal with. This photo shows the surface ruptures that we observed during after the Gorka earthquake in Nepal in 2015. It really induces large loss, including deaths and injuries of local people. And at the same time, what really matters for these hazards is the ground motions. And in order to characterize the ground motions, there are several metrics. One of the most important metrics is the peak ground acceleration, which describes how fast the ground is accelerated. The measured peak ground acceleration during the Gorka earthquake is 2.5 meters per square second. And another interest or relevant statistics is the frequency spectrum of the ground motions. It's widely used for the building design because different architectures are sensitive to different frequency bands. And therefore, what is interesting or unexpected in this earthquake is that because of the local basin, we see an unexpected low frequency ground motion. And this is what I'm also going to deal with in one of my chapters. So in the end, we want to know this information before the earthquake so that we can evaluate the hazard better. And the way we do that is with the earthquake modeling. And in the next slides, I'm going to share with you the major elements in this process. So in the end, we are interested in the infrastructures on the ground surface, but we need to start from the source. Usually the source is known to be localized to weak structures, which we always prescribed it as the geological faults. And there we use the nonlinear friction interaction to describe the locking and unlocking of the faults. After the earthquake occurs, which means the faults are unlocked, it's radiating seismic waves because this process are happening at the time scale smaller than 1 second. And during the wave transported into the surrounding rocks, it's radiating as seismic waves. And in this process, we can expect to see nonlinear wave speed changes. And that's also one of the nonlinearities that we can expect in the process. And in the end, it reaches closer to us where we have very soft sediments. And there, because of the low wave speeds, the wave field are amplified. And therefore, we will see stronger nonlinearities because of a larger deformation from the soils. And that's all the nonlinearities that we can expect. And there are already works on the source nonlinearities and also the site nonlinearities. What I'm going to address in my work majorly is the nonlinear wave speed changes inside the host rocks. How does it look like in reality? Here I show an example during the Tohoku earthquake in 2011. So on the top left panel I show is the wave speed changes before this earthquake. And during this earthquake, the seismic wave passed through the entire Japan, and it induces the local structure changes. And this plot shows here is the distribution of a heterogeneous wave speed reduction in Japan. The more reddish the color, the larger the wave speed reduction is, and it's ranging from 0% to 1%. And we want to understand what is the mechanism behind it. So there are people that did some experiments on the laboratory samples, and with some success. This is one of the examples that have been done by previous researchers. The top panel I show here is the oscillation of the perturbations on the rock sample. And at the same time, they measure the wave speed changes inside the sample. And it is what's shown in the bottom panel here. We do measure a concurrently varying P wave speeds. But what is even more interesting is at the end of the perturbations, there is an unrecovered damage. And that corresponds to what we see in Japan. And this recovery takes a longer time scale than the scale of we apply these perturbations. Maybe it's still not very prominent why this wave speed change is connected to nonlinearities. I will use a very simple definition of the nonlinear mechanical system to clarify this. First, the input of the system is strain, which characterizes the deformation gradient of the deformable material. And the output of the system is stress, which is the averaged force on a certain area. So for a nonlinear system, the response is described as the function of the input strain mapping to the output stress. For a nonlinear system, when we scale the inputs by a certain coefficient lambda, the output is not going to be scaled in proportionally. On the other hand, the scale is going to be a different coefficient, and therefore it corresponds to the wave speed changes. And that's why I'm interested in having a nonlinear mechanical model to describe these effects. I'm standing on the shoulders of the giants, so I would like to share with you what is the state of the art already in this field. So we already observe, as I shown before, the coseismic wave speed changes, but we do not know how to explain it. And at the same time, we also see and observe damage zones existing around the fault, but still we cannot model it completely at a 3D regional scale. And also there are emerging computer power and data that can make the inversion of nonlinear parameters in this process possible, but we are still missing some efficient algorithms to deal with that. And that's to bring this step forward, we are facing some challenges. And the first challenge we are facing is to adequate nonlinear models that can explain both the field and laboratory observations. And the second challenge is about efficient algorithms and software that can help us model the nonlinearities all the way through from source, path to site. And the third challenge is that we have is again, the inversion algorithms that can afford this computationally demanding 3D earthquake simulations. Here is the structure of my PhD thesis. It contains three major elements: the nonlinear rock model, the forward modeling, and the inversion. I did come up with the rock models in chapter 2, and then in chapter 3 and 4, I come up with the algorithms and numerical softwares to simulate this effect in 3D. And in the last chapter, in the second last chapter, I derived the method for the inversion. And then for the applications, for the models, I compared with the rock experiments. And for the forward modeling, I applied it to the Gorka earthquake that I showed in the very first slide. And for the inversion, I applied it to the 2019 Ridgecrest earthquake. The story of nonlinear modeling starts from the model itself. So in the chapter 2, I deal with the nonlinear models. And again, the motivations are to explain the coseismic wave speed changes. And we want to constrain it in lab because there we have a well-controlled conditions where we can better constrain the data. But my contribution in this work is to implement two laboratory-based models in high-performance numerical solver, which is called ExaHype, for 2D simulations. And I compared between physics-based and phenomenology-based models. And in the end, I evaluated the uncertainties in the nonlinear parameters with Bayesian inversion. And this is the first time this kind of model parameters has been evaluated based on statistics in the lab. And I start with again with the observation that we have in the data. We see the concurrent oscillations and also the static drop at the end of the perturbations. The most important part is this, which is not explained before. There are previous models, which is called internal variable model, that explains this. It is based on the law of thermodynamics, and it contains 4 parameters. Out of them, 3 of them can be constrained from the lab data that we used. But this model has some drawbacks because it is not based on some components of the model is not based on the microscopic features. It's rather phenomenology based. Therefore, in this work, we also modified from a previous continuum damage model, which can account for both thermodynamics and also the microcracks inside the rock samples. It is homogenized based on the distributed microcracks. But in this model, it also contains more parameters, but still with the data, we can only constrain 3 out of them. How do I come up with these conclusions? I will show you the data that I used. Here is the experiment setup. It's a rock slab with a dimension of 15 centimeters by 5 centimeters. And in this experiment, we use the perturbation transducers to send waves into the rock sample. And at the same time, we measure the wave speed changes in between T1 and R1 sensors. And to invert for the parameters, we use the Bayesian inversion, and to get the uncertainties of the variables, we take 70,000 2D forward modeling with exahype. And also from data, we can derive the uncertainties and correlations among the different nonlinear parameters. And here I show a comparison between one of the model, which is the IVM model, which has less parameters, and how it compares with the data. We can see a rather good match between the model, which is the blue curve here, and the data, which is the red dots here. But actually, the key concept of Bayesian inversion is not about deriving a perfect matching result. It's about the uncertainties in the parameter space. And that's what I showed two examples from the result that we have. So the first modulus parameter I show here is the damage modulus that controls the amplitude of the wave speed changes. And in this parameter, we see a clear peak in the histogram that corresponds to the parameter range that has the highest probability. But different from there, in this model, there is one specific parameter that is not constrained, which is the time scale of the damage evolution. The reason for this is because the duration of the experiment is actually only 10 to the power of minus 6 seconds. This is much shorter than the recovery process in the rock sample, and that's why it's not constrained. There are some other experiments that can be used to constrain this parameter, but this is not the contribution of our work here. But in the end, we had a model that are constrained from the model, and from the data in the lab, and we want to apply it to the field to see what we can explain. And that's what I did in my chapter 3. Another side effect from these cold seismic wave speed changes are at the ground, where we have a soft sediment. They probably have a large impact on the ground motions as well. In this work, my contributions are to develop a new DG algorithms to suitable for various nonlinear models. At the same time, implemented in SISO, which is the wave propagation software in 3D, and it has the scalability of the code up to 2048 nodes on the supercomputers. And this code is also verified against the analytical solutions and also analyze this convergence rate. In the end, this scalable code finally enables us to model some regional scale earthquakes. I start from the setup of our models. So in this earthquakes, I use the kinematic source model, which means I only prescribe the slip rate on the fault instead of describing it with some physics laws. And here I show the map of the fault slip. The darker the color, the larger the fault slip. And with this sources, we injected it into a simulation domain, which here is a layered model which contains 5 geological units. Among them, there is one special layer, which is the sedimentary basin. It has a very small size. The depth of it is varied from 0 to 350 meters. This is particularly small if we compare with the entire simulation domain, which is a few hundred kilometers. The other feature of the basin is that it has a very low wave speed. It is only 200 meters per second in shear waves, which is 1 order of magnitude lower than the bedrocks. And this low wave speeds would induce strong nonlinearities, and that's what this is what how we account for this. And we constrain our model again through a widely used engineering shear modulus reduction curve, which describes how the modulus are reduced with the increase of the strain. In this model, when we have a large strain up to 10 to the power of minus 2, the reduction can be as large as 80%. And the entire simulation domain contains 2 million tetrahedral elements, and they can resolve ground motions up to 0.5 hertz. And what we can model with this, it is actually the very first time that we can see the cold seismic wave speed changes in 3D in the subsurface. What I show here first is the depth slice at 12 kilometers. But what you see here is the distribution of the wave speed reduction around the fault, marked by this dashed line. The largest reduction is at around 10%, and it's actually correlating with the fault slip. The larger the fault slip, the larger the reduction. And also another interesting feature is, or interesting question is, what is the range of distance we can measure the wave speed reduction is measurable? In the field, the measurable amount is 0.01% from the seismometers based on the interferometry method. And in our model at this depth, we see we can still measure it until 70 kilometers away from the fault. But if we move to a shallower depth, which is 2 kilometers, we see the range of measurable reduction is larger, which this time around 100 kilometers. But what do we, this is from the model, but what do we observe in from the measurements in the seismometers? Actually, this value is much larger. In this case, it's 2 orders of magnitude larger. How do we explain this, or why there is such a difference? Maybe we can understand it from the actually wave reduction inside the sedimentary basin. This is again from our model results, and we see inside the basin we have a reduction up to 88%, and it has a very heterogeneous distribution. It's correlated actually with the basin depths. The deeper the basin usually comes with a larger modular reduction, and that's where the wave field is more amplified. So with these results, we propose a hypothesis that is the measurement from the seismometers probably is actually a depth average reduction, and this reduction is mostly contributed from the shallow sedimentary layer. So far, we see strong nonlinearities in the basin, and we are interested in to see what's its impact on the ground motions. That I'm not going to show you here. This is I show one of the the velocity time series at one of the stations inside the basin. We low pass filter the signals by 0.5 hertz, which is the resolution of our model. And here I show a comparison between the elastic model and the nonlinear model. The nonlinear one is in red, and we can see a prominent attenuation that is correlated with these wave speed changes. If we put it into the frequency domain, we can see the nonlinear model is amplifying or adding to lower frequency components. And we also put the data in frequency domain at this station to see if we can actually measure this. Yes, we see a lower frequency compared to the elastic case in the data. And that means this frequency shift due to the nonlinearity is actually measurable. At this point, we see strong nonlinearities close to the ground. Another interesting question that is what is impact on the source, and that's what I did in the fourth chapter. Again, the motivations are from the observations. We see the faults are not a single plane. It's surrounded by some damage zones. We don't know how it's co-seismic generated, and we also cannot model it yet to study the earthquake dynamics and seismic radiations due to this generated fault damage. In this work, I again implemented a nonlinear model that is also describing the post-failure of the brittle rocks. That's important for simulating this fault damage. And also we adjusted for dynamic property simulation. And also, again, we verified the code and we studied the impact of this damage on single fault and on fault interaction. I will start from the results on a single fault. So what I show here is the shear modular reduction next to the main fault plane. And we see some localized structure with high damage. And these are called the shear band next to the fault. And the angle of the shear band is actually correlated to the background stress orientations. We verified this orientation against analytical solutions, and it's matching well between the numerical results and the analytical results. Actually, during the formation of the shear bands, it comes with other high-frequency seismic radiations. And that's what I'm going to show you in this video. It's a velocity field during the rupture of the earthquakes. And what we see here is as the shear bands generated, it's radiating high-frequency signals. And that's what I show that's one of the results we obtained for a single fault. And the next question that I would like to share with you, or that we have, is about how this shear band is influencing the fault interaction. To study this, we use a different setup which contains 2 fault planes. They are 2 vertical strike slip faults, and they're separated by a certain distance. In this case, it's 3 kilometers away from each other. And we nucleate the earthquake on one fault, and under certain conditions, the rupture can jump to the fault 2. And actually, what is interesting here in our work is we see the alpha damage can facilitate this jump, but also, and at the same time, it comes with a delay time. And that's what I'm going to show you in the next animation here. The top panel is the shear traction on the 2 faults, where the bottom panel are the slip rate. I'm going to play it. We see during the nucleation of the first fault, we see a dynamic, okay, it's very blurry, but we see some dynamic perturbations on the second fault. But at the same time, well, after a certain time, when the damage is reaching the second fault, we can see a high traction shear front forming, and that's when the fault is going to rupture again. And that's what I mean. With the alpha damage, we see a facilitated jumping, but it also comes with a delay time. That's very interesting because in the field, we also see earthquakes that are delayed for a certain amount of time. For example, in the retract earthquake, we see a foreshock that is magnitude 6.4, which occur 34 hours before the main shock, which is all, so that's probably related. And maybe you also want me to give you a maybe first order explanation to this phenomenon. I think it's better to see it in another perspective. Here I show you the depth slice at 7.5 kilometers, and that's where the shear band is expanding from fault 1 to fault 2. Within this shear band, we have a lower modulus, and this lower modulus cannot support as high shear traction, so this traction needs to be distributed to its neighbors, and so that's where the fault nucleates. This higher shear traction next to the shear band nucleates the fault 2, and that's that's our most interesting findings in this study. So far, I show you nonlinear models, but it also introduces more parameters to be constrained. So in the next chapter, we spend some efforts on developing a method and testing it to see how much we can constrain the data. And as I said, the motivation is to constrain those nonlinear parameters. And my contributions in this part is to integrate multi-level Bayesian inversion algorithms with rupture dynamics. And also we verify the accuracy and performance, including a full machine runs on the Frontera supercomputer. That's what is needed because the Fourier simulation is very expensive, and we need a lot of resources to actually constrain the data. And then we applied it to the 2019 Ridgecrest California earthquake. In the end, we constrained the uncertainties in the parameter with the physics-based earthquake modeling. Before I delve into the inversion results, I would like to first give a brief introduction to this earthquake. So this, as I mentioned, this is the earthquake I mentioned before. It's the main shock of the earthquake has a magnitude of 7.1, and the red curve here is the main fault that hosted this major shock, this main shock, and the other conjugate and subparallel fault system here hosted the foreshocks, and also this segment here also was part of the main shock as well. So that's the earthquake, and there are before my work or before our work, there are already very interesting model, dynamic rupture model that are constrained with rich data from including the velocity model, the stress field, and the seismometers, and also geodetic data. But there is one special drawbacks in this study is there's only one realization, and we don't know the uncertainties in the parameters. And this plot shows what we can actually model with the dynamic ruptures. So we can model the fault slip from green to yellow, I show here, and also we can model the alpha plastic strain, which describes how much inlet deformation we accumulate during the rupture process. So in this work, we want to constrain the uncertainties and parameters. And to reach this goal, we combined the GNSS displacement. These are the stations I show here. The pink rectangles are the high rate GNSS with the displacement time series, and the static, and also some static GNSS stations where we only recorded the coseismic displacement vectors. And another set of data we use is the fault parallel offset measured with the satellite imagery. There are many outputs from this, but I don't think I have time for all the results. I'd like to explain one interesting feature that we can uniquely answer with Bayesian inversion. It is how certain that we are that the shallow slip deficit can be explained by coseismic fault slip. I think most of you are not familiar with this concept. The shallow slip deficit is a reduction of the measurable fault slip near the surface. To bring this more concrete, I use this plot. This is the x-axis is a fault slip, and the y-axis is the depth. And what we see with this yellow curve is the preferred model from our inversion. And what we see here is at the surface we have a smaller fault slip compared to the maximum fault slip at depth. And this difference are what we call shallow slip deficit. From the inversion, for the 4D Bayesian inversion for this setup, we only need 600 samples. And this is particularly a lower amount. It's 2 orders magnitude fewer samples. If we compare with our what I did in the first chapter is 70,000 samples. And that's the merits of the Bayesian inversion algorithm that we used in this work. From the inversion, we can derive the preferred SSD is 13.1% with a standard deviation of 5.1%. And the question is how much this is matching the observations. We can use the histograms of the SSD to answer this. From the observations, we see a variation of the SSD between 8% to 32% for this specific earthquake. And in our inversion, 55% of the models fall in this range. And that's, or put it in another words, is that from the geodetic data, the possibility that the observed SSD can be explained with the physics-based model at the coseismic phase is 55%. And that's the first time we can quantify these answers for such kind of earthquake features. So at this point, I would like to conclude my presentation. The first chapter of my work revolves around the nonlinear models and the lab data. And second part of my work is about new algorithms for both wave propagation and dynamic oscillations, which are the 2 key elements in earthquake modeling. And in the last component, I integrated efficient Bayesian inversion algorithms with the earthquake simulations to try to constrain some parameters in its nonlinear processes. And that's it. I'm looking forward to discussions. Thank you.